I did a rough calculation of how much time I've gone over, and it's significant. So I felt guilty. And then feeling past. But the most serious consequence of me going overtime is that I'm getting low on notes, and I don't want to write any new ones. So we have 6 lectures left.
Including today?
Yeah. Right? That's right, right?
I don't know.
The semester ends like the 4th or something. So I'm going to give you 4 more lectures, including today. So let's see. So that's today. So the 17th. That's so Thursday this week. I'm going to take that one off. Let's see, the 22nd, which is next Tuesday. So, yeah. 22nd we'll have class, and the 24th, which is Thursday. And then the 29th, which is Tuesday. If I remember, I'll send an email, but I might not. And the 31st is the last day. Class plus, that's your homework 5 due. And then on the, so that's March, April 12th, which is a Tuesday, is when your project's due. Somebody asked me if they can just email their code to me for the project, and the answer is no. Basically, I want like a report. Hopefully something you can email me or else drop off. But you know, plots, discussion, that type of thing.
Do you also want the code then?
Sure. I'll totally read it.
Oh, it's so hard to grade coding assignments if you don't have a code.
Yeah, because you never run the code.
Yeah. You run it, you make some plots. I believe that it's your code. All you're doing is all you do when you send it to me is confirming that you wrote the code, I guess. I don't know. Yeah, send along. I've looked at them in the past. If there's like a major bug in one of your questions. So that's 1, 2, 3, yeah. Okay, so that's 4 more classes. To do your assignment 5, I want to talk a little bit about gauge invariance. So I'm going to do a bit of electrodynamics and gauge invariance today, and then let's see. And then next Tuesday, I'll start into Z2 gauge theories. We'll do them on a lattice. That's kind of fun. It relates to like the surface code some of you guys are working on. And then I'll probably end up with a little bit of discussion about entanglement and free and interacting field theories. So there's not much left in this class. For me, lots left for you. So let's review what we know about Maxwell's equations and electrodynamics, which for me is very little. Who takes E&M in grad school? 1, do you? Take Jackson?
Yeah.
Yeah?
We didn't get very far.
Like how far? Like. Okay, that's cool. We had to take 2 semesters at Jackson in grad school in the States, but I don't remember anything. So I had to look it all up again. So let's just start with, the only thing we need is sort of the Lagrangian for an electron, a spinless electron in an electric magnetic field. Isn't E&M required? Isn't it a core course?
You only have to take like 2 of the core courses. There's like 6 core courses, and then
There's 6 core courses?
There's like a list you can choose from, and if
I see,
you're
so it's
in
an
the
option to not
IGC,
take
then
it?
you can take only 2 of them.
Oh yeah, because you guys have quantum information processing, right? That's a core course?
Yeah.
Missing out.
Are we though? On the 1 chapter of Jackson.
The 2 chapters.
2.
All right, so basically all you have to know is that you can write electric fields and magnetic fields in terms of scalar and vector potentials, right? I guess I barely use what I learned in E&M except for gauge theory. So like basically what we're doing today. So I guess you could just skip that entire course.
Can't know that we have this lecture on gauge
Yeah,
theory.
that's everything you need to know. I don't think I'm writing these with vectors, okay. So A is your vector potential. Phi is your scalar potential. That's a time derivative of the vector potential. And that's your B field, and that's your E field. Does that look vaguely familiar? Okay. Good, because that's like the first thing I wrote in my notes. So I can't go back any further. So there's a classical Hamiltonian that describes, the motion of a charged particle with charge Q. Oops, that's a P, that's your momentum. A depends on space and time, in principle. I guess I could write that. Q is your charge. The scalar potential also depends on space and time. And this gives you your Lorentz force. Right, which is basically the equation of motion that comes from that. I won't use the force version of this. This Hamiltonian, you'll see this written quite often if you deal with, charged particles and magnetic fields. So I'm going to do an example at the end of class on Landau levels. What a Landau level is it's basically an energy level that occurs when electrons are in 2 dimensions, subject to a magnetic field. So for example, we'll mostly set that scalar potential to 0. So that gives me a vector potential only. If I expand the Hamiltonian, I'll get something that looks like 2q, what do I want, A dot P maybe? Okay, so as you know, the only thing you need to do to go to quantum mechanics is replace this with minus h bar grad. minus I h bar del, which gives me I'll put a 2 here. 2. Okay, so what? So what's so good about that? Well, I can basically write this as minus 1 over 2m okay, so that's the simplest way to maybe write that Hamiltonian. And in 2 dimensions, oh, I said h bar equals 1. That happened quick. Right. In 2 dimensions, we're going to deal with this Hamiltonian. So when we only have an x and y coordinate, it'll give us something like this for the Schrodinger equation. Where's my 1 over 2m? So I'll just put it here. Okay, so that's basically the simplest way of putting quantum mechanics into the Lorentz, force, if you will. We'll come back to this. What I really want to talk about is the gauge transformations, which, the gauge freedom associated with the scalar and vector potentials. Okay. So as you know, you can transform A and phi with some more or less arbitrary gauge while keeping, the magnetic and electric fields is the same. Okay, that gauge transformation of the potentials looks like, I'll say, the transformed potential, call it A prime. It's just A plus grad chi, I'll call it, for the gauge field. In component form for this one, just imagine mu running over your spatial indices for now. I could also write this like this, say. And then the scalar potential, I think this one's a minus sign. Okay, just has the time derivative of that gauge field. And that thing's a scalar, remember. Okay, so if you plug that into your expressions for B and E, remember, you'll see that those fields are invariant under this gauge transformation. So in quantum mechanics, we can have a gauge transformation as long as it keeps the, if you will, equations of motion invariant. And that means that the transformation associated with that gauge on the wave function has to be like a unitary. I'll call it a physically equivalent set. So I have some gauge transformation to wave function psi to psi prime, a to a prime, phi to phi prime. That leaves the physics invariant, you know. So as we know for quantum mechanics, that can be accomplished by, or at least the wave function transformation can be accomplished by a unitary. So we want some sort of unitary operator, basically, that corresponds to, like, you know, this gauge transformation here. Make sense? So the easiest way to write that unitary is to just assume that transformation is given by something that looks like e to the I to some gauge field. So that the way I'll write it is e to the I, Q is that charge that occurs in the Lorentz force. And this is my chi, which is that same scalar field essentially. And you know, as I'm writing in the classical Hamiltonian, the scalar and vector potential as a function of space and time, so should this be a function of space and time. X, R, whatever I want to call it. So the fact that this chi depends on the coordinates makes it very different than, I guess, just like an arbitrary phase associated with the wave function. And we'll see why. But this type of, I guess if you want to call it like a local phase, is the hallmark of a gauge transformation. It's a local, if you will, U1 transformation. So gauge theories correspond to theories that have certain like symmetries that have local invariance. Is one other way of kind of looking at things. So like in your Ising model, you have a global, say, Z2 invariance or something like that in the Hamiltonian. If I constructed a model that had a local Z2 invariance, so just on a bond, or as we'll see next time on a plaquette on the lattice, then that local invariance or that local symmetry is what defines a gauge theory in that sense. So it's the same theory. I have this U1 transformation that changes depending on the location.
Or gauge symmetries are not real symmetries, right? Like for instance, in the Ising model, set 2 symmetry gives you information about physical models, but in here, like local symmetries are just redundancies of your description. Right?
Yeah, they're not. Yeah, so that's exactly right. So they don't give you. Yeah, so you're breaking when we're breaking a symmetry, like when we do spontaneous symmetry breaking. That's a local. That's a global symmetry of the Hamiltonian. So what these gauge transformations give you, these gauge symmetries. So what you'll see in the Ising model case, which I think is somehow, it's more intuitive for this class, you'll see that instead of having a symmetry broken ground state, you'll have an extensive degeneracy of equal energy states in the ground state. So the gauge, the local symmetry, resulting sort of killing the spontaneous symmetry breaking. Yeah. Okay, but as you'll see on your assignment 5, there are physical consequences of these gauge theories. So that's basically what the Higgs mechanism is. It has to do with spontaneous symmetry breaking and these local gauge transformations. So the problem with this type of gauge, if you will, is that it sort of screws up your Lagrangian, the one that we're used to dealing with. So. So the problem with the Lagrangian occurs in the derivative. So what was it? Minus I q chi. Oh, I forgot the q. Okay, so that term occurs in the Lagrangian, right? That's just all the space-time derivatives. And here I've transformed my wave function, right? It's a unitary. Okay, so you can pull this I q chi out. You'll have a derivative of the field, as usual. But then you'll also have a term that's like I q derivative of that thing, right? Because this is a function of x and t. So that thing's a problem. That derivative connects, as you know, you write the derivative in terms of sort of a finite difference of field values in space and also in time. So in your path integral, that type of derivative of chi, of the gauge field, will connect the fields at different space and time in a non-trivial way. That's path integral. x and say x plus dx in space and time. So if I just use a Lagrangian of that derivative, you can expect some sort of change to occur in your path integral. I don't know what that is yet, but I don't care. So we need a different definition of the derivative, essentially. So we can get a locally gauge invariant description if we just modify this. So I'm going to say if we replace everywhere in our Lagrangian, that derivative by, I'll call it big D. Okay, if it's acting on the wave function, it's my usual derivative. I'm going to explain these indices a bit more in a minute. And I'm going to subtract off IQ A mu. Okay, you should basically, where did I write that last? Okay, I wrote this for a reason. This is basically what's motivating this change in derivative. So if I operate on the gauge transformed wave function with this derivative, we can see what we get. Again, I'll be able to pull out, okay, that local gauge field. And I'll get that term down there. IQ D, okay. And then I need this piece here, so. Okay, so if I pull terms together, I should get this, plus or minus, plus. Okay, and that thing looks much better because, number one, I have my derivative with a big D, right? Which is just giving me, something that has, this local phase, which will be a unitary when it'll leave that D psi term invariant. And then also, this is just the usual gauge transformation that I already wrote for the vector potential. Which we already know leaves the equations of motions invariant. Okay. So that's a really quick and dirty motivation for what's called the covariant derivative. And by just defining this local gauge transformation here, which is all I've really done, I've essentially shown that this term that we derived in the Hamiltonian through this quick quantum mechanical substitution will give us essentially the proper derivative in the equations of motion, and the correct sort of gauge transformation for the potential. Okay, so when you write that Lagrangian, when you write a Lagrangian for these gauge theories, that's the term that you need, that little bit of extra term in your derivative. So once you start dealing with these, haven't been very careful with basically what these indices mean. I'm just saying they're space-time derivatives. But which metric you're in matters, whether or not you're in Minkowski space, which is real time, or Euclidean space. Because as we saw when we looked at the mass term, when we derived the Klein-Gordon equation, to get the signs right, you have to basically be careful with how these derivatives are taken. And actually, that's where this word covariant comes from. So just an aside. So we can write the potentials as a 4 vector. I'll call them who's never taken relativity? Ever? Okay, so this might look a little weird to you. So what I've done is I've just defined a vector that has a, in relativity it's like CT is the 0th component, and then the 1, 2, and 3 components of the 4 vector are x1, x2, x3. All right, so Maxwell, Lorentz invariance and C and everything's built into Maxwell's equations, and so the same formalism can be used in electromagnetism. So it's the potential, which can be written as a 4 vector with the scalar field as the 0th component, and then the vector, which is like a 3 vector, is the 1, 2, and 3 components of the 4 vector. That sounded weird when I said it. And then, whether or not these coordinates are basically subject to, transformation via a metric can be written very concisely with keeping track of these indices. So for 4 vectors like this, recall there's covariant and contravariant indices. Which means for any 4 vector, if I write it as a superscript, with raised indices, it looks like that, and covariant. Right, and these are annoying because they're not powers. All right, don't forget that. Covariant, contravariant, and they're related by a matrix transformation that I'll call the metric, because that's what everyone calls it. So the matrix G can raise or lower the indices. So this defines and the metric's just that sign structure, whether or not it's Minkowski for us or Euclidean. But of course, when you get to general relativity and stuff, the metrics can become quite complicated. So relativistic. So for curved space, these things are complicated, but for flat space, they're easy. There's a sign convention here. Oh. So it's a diagonal matrix with the sign structure of your, basically derivatives in your Lagrangian, which is essentially the relationship between, Lorentz invariance and your field theory, remember? You set the speed of light equal to 1 in this case. And so this is the proper metric for when we deal with the real-time evolution in our path integrals. And why we need this, again, it's the same as when we derived the Klein-Gordon equation, or the same as when we derived the mass by comparing it to the Klein-Gordon equation. Is that in order to get the right signs in your derivatives, we essentially use this metric. So by definition, you get minus signs in the space components, and similarly in the time, in the time component you get no sign change because of that +1. And for your derivatives, you get minus signs out front of just the space components. Right? So this is what gave us remember when I derived that mass, I wrote it like this. I can't remember which way I wrote it. One index contravariant, one index covariant. That'll give us the right signs. Remember, it's a Lorentz invariant, but C is equal to 1 minus sign for all the space components. What's this thing called? Is it square, square, cube, or square, squared? Nah, that'd be weird, right?
I think it's just a square.
Just this thing? Yeah. All right, whatever that stupid thing is. Okay, so basically that metric, right? I mean, when we Wick rotate, remember this picks up a minus sign when we do the Wick rotation. And the minus sign falls out in front of the action, okay? But this is just the way that we keep track of that those plus and minus signs when we're doing stuff like this gradient term. So the same thing will apply in your covariant derivative. Okay, you can have upper and lower indices on that. So that was Minkowski space. And then if you're in Euclidean space, so that's, if you're looking at the partition function or thermodynamics, then there's no need to distinguish between contravariant and covariant. Okay, so the indices are all the same. Okay, so just keep that in mind if we're dealing with real-time evolution. You'll often see, if you actually read a textbook, you'll often see the all the derivatives, if you will, written in terms of something that's like this contravariant covariant form here. Okay, so the last little piece to lead into your assignment 5 that you have to know from essentially gauge theory is the rest of the form of the Lagrangian. So just back to E and M for a moment. All right, so I wrote E and B in terms of the potential 4 vector, if you will. So you can combine E and B into a type of 4 matrix. I don't know if that's the right word. It's a tensor. It's the electromagnetic field tensor. And that thing's just defined. I'll do the contravariant case. Right, where each one of these is now components of a 4 vector. Right, so. So just a nice compact notation for what turns out to be a matrix. I think the signs are right. It's 0 on the diagonal. That's the contravariant form. If I did the covariant form, you switch the minus signs on the first column in a row. So that's just a definition of F, the electromagnetic field tensor. But F gives as you will derive in an E and M class exercise, Maxwell's equations. Which you can write sort of very succinctly. Let's see, alpha is 2 equations. Where the latter equation is written in terms of a current density. With 4 vector, your usual charge density plus the 3 vector current density. Okay, no, I'm not going to use Maxwell's equations, but that's why we define the electromagnetic field tensor. So that's something you'll do in E&M class. But all I want to do with the electromagnetic field tensor is just write down the Lagrangian that comes from it. So what I'm basically doing is deriving, the Hamiltonian or Lagrangian or the Lorentz force that I wrote on the, on the chalkboard right when we started the class. And so if you have this electromagnetic field tensor, so if you're in this covariant formalism, then the scalar Lagrangian comes from a term that looks like There's only so many ways to make a scalar actually out of this f, so you can just try a couple and you'll find the right one. So I've set my current densities equal to 0 here. That's a scalar quantity. And it's essentially your Lagrangian. If you take that Lagrangian, you'll see it's very close to the Hamiltonian in the usual way. You can derive the equations of motion from that. So I'm just writing down basically this covariant or this 4-vector form of the Lagrangian. So again, show that this recovers the classical equations of motion. Just write the Euler-Lagrange equations associated with that. So now when we're writing our path integral, when you're looking at this problem on your assignment, you'll use the general Lagrangian that also has the the space-time, if you will, fluctuations in it. So it'll be something like this covariant derivative. That's your field now. This isn't your, you know what it is. So it's basically just the usual potential piece, if you will, plus the covariant definition of the derivative, plus you can add any sort of terms that you want that give you any potential.
You mean the integral of d mu phi, right? Because d mu is not real.
Oh, sorry, this thing. Okay, so that's, again, that's a very quick and dirty motivation for your Lagrangian. But that's the object that you're going to consider on your assignment 5. So it really is just sort of, in some sense, the Lagrangian of the gauge field, if you will. Questions on that? Again, I think the kind of most important part is this motivation of the covariant derivative, really. Everything else comes from, I don't know, it's like everything somehow came from classical physics. But. So when you look at your Lagrangian, you have space and time, right? And that's how the quantum mechanics comes in again. I mean, this covariant derivative has to come from quantum substitution, but then all you do is you have you can rederive the entire path integral in the usual way, and you get real time, or you can Wick rotate into imaginary time, and so on. Okay, that should be enough for you guys to derive the mass of the Higgs field in your assignment, which is like the only fun thing left to do in physics. No, just kidding, I want to do something fun. Any more questions on this? Since we're talking about E and M today, I just want to derive Landau levels and talk about the integer quantum Hall effect, because we're so close to being there already in this lecture. The integer quantum Hall effect is an experimental phenomenon that, if you measure the resistance transverse to an electric field in a 2-dimensional electron gas, you see plateaus at certain values of of a magnetic field that's applied along the z direction. This was a Nobel Prize winning experiment. And the explanation, I mean, it requires quantum mechanics of a many electron system in 2 dimensions. But sort of conceptually, or intuitively, it's quite nice. So let's take our, let's back off from the field theory. Let's just take our Lagrangian. Let's just look at our regular Hamiltonian, or classical Hamiltonian, and see how we can understand this integer quantum Hall effect. And the first step is to discuss Landau levels. Not to be confused with all the other Landau things that we see in this class. As far as I understand, Landau levels were derived in like a textbook by Landau from the 30s. Okay, so there's nothing new under the sun here. What we're looking at is that 2D Hamiltonian that I already wrote, essentially. So 2D electrons, okay, I'm just going to call it a gas. It's just a system living in the xy plane. Seems experimentally unfeasible, right? It's actually not. They grow these things in semiconductor heterostructures. Take like a junction, really pure semiconducting substances, and you get a nice 2-dimensional electronic plane that's essentially a gas. These things are quite easy to make now. So if I'm living in the xy plane, that's where all my electrons live. Let me place a field perpendicular to the z direction. Why did I draw like this? X, Y, Z, B. Okay, so the system's 2-dimensional, but there's a field coming out of plane. Okay, so I know my equation of motion. I know my Hamiltonian. I'll write it like this. Let's use the charge of the electron, which is minus q. From my equations previously. And let me choose a gauge for my vector potential. And I'm going to choose what is originally called the Landau gauge. Remember, my field has to be invariant. So it's invariant under the different gauge choices. So the physics of the problem won't change if I choose my A vector to have one component in the y direction, which is the magnitude of the field times x. And just check that gives back, oops, the proper magnetic field when you take the cross product. Or the curl, sorry. So this will give me BZ. It's just a convenient gauge to work in. That's what gauge freedom gives you. So I can rewrite this Hamiltonian. Remember, it's only 2-dimensional, so I have 2 momentum components. This cross term was minus 2q. And the gauge. P right? And the dot product of P, Y, and the gauge is the only non-zero dot product, so that'll be just the PY component there. And then what? And then the A squared, so that's possibly correct. Fill in all the steps. So the nice thing about writing, the nice thing about that gauge choice is that it gives me just this term when I take the dot product. So I only have PYs, I have PXs and I have X's, but I have nothing that doesn't commute with PY. So the Hamiltonian commutes with the momentum in the Y direction. Whatever. Operators. No, I'm using those for unit vectors. So we can basically replace the momentum in the Y direction with its eigen values, right? I'll write them in terms of K's. So this is an operator. This is an eigenvalue of that operator. Then I'm going to rewrite my Hamiltonian. I have the X piece. Okay, so these three terms will give me, so that's my PY squared. Yeah, it looks right. Something like that. Let me write it like this. So let me pull out that E squared, B squared, 2M, X. Oh yeah, I forgot to replace my PY. So KY, EB, squared. Yes. That's what I want, because now I can replace E, B over M with something I'll call omega. What's omega? Cyclotron frequency. Sounds so awesome. It's called this for a reason, because that Hamiltonian is basically exactly the quantum harmonic oscillator Hamiltonian, which you're used to seeing written in terms of some omega. And so that makes the problem really easy to solve. And the only weird thing is that the minimum and the potential has just been shifted over. Which seems like no big deal when we call it x naught. Just a constant shift in the minimum of the potential to a different value of x. So the energies, all right, so I have something like one half m, I'll keep my x label, plus 1/2. That's m omega cyclotron squared, x plus, what do they call it? X naught. All right, doesn't get any easier than that. So the energies are given by h bar omega, n plus 1/2, where n is integers, greater than or equal to 0. 0 is included because of boundary conditions. And that's it. So the energies are given by this, but we have a ky dependence. You know, we have a momentum dependence still. So the wave function basically has to have this quantum number in it, but it doesn't affect the energies. So it just occurs in this offset. Okay, so we get massive degeneracies at each one of these energy levels that I'm describing by n. So since they don't, so since the energies don't depend on ky, that's where the degeneracies come from. So the actual wave function, the two-dimensional wave function, has to have ky basically in this type of plane wave form multiplied by the, say, x wave function, I don't know, x minus x naught wave function coming from the simple harmonic oscillator. I mean, if you just do the one-body problem, that's what will come out. That's like, the interesting question is, what is the degeneracy of each level? Okay. These are the Landau levels. Each one of these levels is a Landau level. It comes, specifically from having two dimensions and using a gauge to give you a term that only depends on py so that you can do that commutator. That's where Landau levels come from. So once you have Landau levels, the question is, who cares? So what do they give you? Well, so the degeneracy of each level is important because you can only fit so many electrons into this many particle wave function. Because each electron has to take a different state because of the Pauli exclusion principle. And then, when your level is filled, in order to put an electron into the system, it has to jump to the next n value. That's how Pauli exclusion works. So what is this degeneracy? All right, so I have x and y. I have a solution that has my ky in it. So let's do something completely experimentally legit and assume periodic boundary conditions in the y direction. This will just give Ly is my linear dimension, Ly, Lx. Okay, so it's the physical dimension of my system. Okay, so essentially just because I have this type of exponential solution, this will give me I'll call it nu. It'll just give me constraints on the values that ky times Ly can take, as usual. Right, so the wave function's periodic because of that exponential, 2 pi nu. Okay, so that's basically the nu's labeling these states, if you will. But we have to be careful about the x direction. I mean, I don't have this type of wave function in the x direction. I have a simple harmonic oscillator wave function. But the constraint that maybe isn't obvious but important for this type of wave function is that I have to make sure my center of my potential, or my potential minimum, occurs somewhere within the sample. Basically, so the orbits of the electrons are contained within that sample somehow. So that shift in the wave function, physically matters because of that reason. So that x naught actually haunts you a little bit. Okay, so the physical position of x naught, has to be somewhere within the linear dimension of that sample. So the electrons that we're considering, if you will, orbit that potential minimum inside the sample. I think both of those require a bit of thought, but it's nice that essentially all the interesting physics of the Landau levels and the integer quantum Hall effect comes from the constraints. It comes from the boundary conditions of the solution, which is usually the case in quantum mechanics, right? So this x naught now, okay, so how did I write it? Okay, h bar.
Roger, if all the interesting physics comes from the boundary constraints, and you've essentially chosen a boundary in the y that's not easy to
real
do, then how come you can see these things experimentally?
Actually, the experimental detection is a little bit complicated. This periodicity is actually broken not because of the boundary condition, but because of impurities in the sample. So this is like a way too easy simplification.
Okay.
All this boundary condition does is give you this consistent, this sort of simple, self-consistent wave function. So yeah, maybe I shouldn't have said all interesting physics, but it's just like the important relationship between quantum numbers in some sense comes from boundary conditions in the problem. When we look at quantum mechanics, this is another case, I think, of it. The solution itself is somehow simple, but the interpretation of the solution, through the boundary conditions is what's interesting here. Experimentally, things are way more complicated. I mean, these levels are smeared energetically because of disorder in the electron gas. And so what you actually see here, I mean, I think it gives you a hint for the problem, but to solve it in detail requires all sorts of ways to deal with this disorder and so on. That's like the bane of condensed matter physics is disorder. Who called it dirt physics? It wasn't Anderson, was it? Am I being recorded? solid state physics always got a bad rap because in order to, it's very hard to go from sort of clean derivations to what people see experimentally, I mean, historically. So integer quantum Hall effects and fractional quantum Hall effects, the thing that we're kind of deriving here, they were really seen when people made ultra pure samples. And samples, how do you make a two-dimensional electron gas? Like I say, you basically have to have the semiconductor industry made it capable of fabricating really high purity semiconductors that you can make these heterostructures with, right? So experimentally, that all came from some industry history that's tied to making computers and all this type of stuff. And then basically you needed these ultra pure heterostructures and very low temperatures. So you had to have like really good refrigeration technology, and that gets your temperature below h bar omega. And so there's all sorts of complicated things that went into this. So the experiments, I think, didn't come out. When was the integer quantum Hall experiment? 85. That's when the Nobel Prize was given. But I think it was 1980. It's not that long ago, right? So there's lots of complications. This is just the theorist's dream. I've rewritten my x naught in terms of, I put Ly back into it, okay, for my relationship with nu and ky. Okay, so my condition on x naught then becomes a condition on nu, right? I just rearrange that inequality. It'll give me m Lx Ly 2 pi h bar. And let me get rid of that cyclotron frequency. So instead of the maximum extent of x naught, right? I've written this essentially in terms of the number of electrons I'm putting in the system. This is the maximum number. So I've changed that inequality to be an inequality on the maximum number of electrons. Right, and it depends on the size of the sample and the magnetic field. Okay, so that's kind of the gist of the filling factor, they call it. So you can define a ratio. I already used nu, which was a mistake, because that's usually the filling factor. So let me call this thing nu max. So nu tilde is just a number of electrons that I'm jamming into my sample. Over, the maximum for each Landau level. Right, so when this thing, the filling factor, is an integer number, it means I have the first Landau level filled, I have the second Landau level filled, and so on. Oops. The first is, yeah, I guess so. Landau levels. So if I want to put an electron one more electron in the system, if I'm at perfect integer filling factor, I have to jump that gap, right? H bar omega. Landau levels are, okay, that's just Landau levels. Whatever, it's just a solution to the simple harmonic oscillator, basically. But they give you the integer quantum Hall effect. So if I take these semiconductor heterostructures and I apply an electric field in the y direction, okay, that's my x direction, y direction. And then I guess my field, I put a magnetic field that's coming out in the z direction. BZ, coming out of the board. Then the integer quantum Hall effect is a statement about the measurement of the resistance or the conductivity of the sample in the transverse direction, in the x direction. Just like the regular Hall effect. So in the Hall effect, you basically use this Lorentz force to show that you have current components in both the x and y directions. Y is obvious, right? So the current density in y. It's just given by Ohm's law. I'll call it JY. So that's just the conductivity of the electron gas, just the usual conductivity. If I had no magnetic field, all I would have is that current density in the direction of the applied electric field. Okay, I'm not going to derive the Hall effect, but so classically, in the classical Hall effect, the electron trajectories are curved by that magnetic field. I'm doing the right-hand rule or something, right? And so that curvature basically gives you a conductivity in the x direction. I derived the current, or the conductivity tensor. Let me just show you how to do it. In case you want to. I'll post these notes online. This isn't a class about the Hall effect, I guess. So let me define an electric field. Which is basically like, you know, the electric field that's felt by the Lorentz force. So I call it E prime. It's going to be this V cross B term. So it's just going to be the current density times the magnetic field over NE. Because my current, I've called the number density minus the charge. Okay. So that's just a number density. Of the electrons. Okay, so let me just real quick show you what the total current is. The important point is how it depends on sigma naught, which is the conductivity, it's like the underlying conductivity of the gas. just write it like this, NE. So that gives me a definition of a conductivity tensor that has off-diagonal pieces that depend on that sigma naught. This will give me my X and Y current densities through Ohm's law, but I have nothing in the X direction. Okay, so you can get all these steps from the Lorentz force. So what we find is we'll have a current density, which I'll use to define. I got to invert this to define the conductivity tensor. Which has interesting components. So if you invert these equations, the xy component, importantly, we'll have something that's like sigma squared on top and sigma squared on the bottom. Well, the yy component, we'll just have the sigma naught and the same denominator. So that's the important part of the Lorentz force. So that's basically just the Hall effect. So the important sort of quantum mechanics is something we cover in condensed matter. It's basically the form of that sigma naught in a electron with electronic gas with some disorder. So let me just note what that looks like. So the Drude model implies that the conductivity has to do with scattering off random impurities. And the less you scatter, the higher your conductivity. Basically means sigma naught will be proportional to some mean time between collisions. So this is just some phenomenological input to this discussion at this stage. So this is what I'm measuring. I'm going to measure the components of the conductivity. What that tensor means, of course, if I have a voltage in the y direction, I want to measure the the x direction of the current, and that will give me the Hall conductivity. This is just the one in the y direction. So let's go back to the Landau levels. So what happens if I have this two-dimensional electron gas? If I just think of my total number of electrons, the thing I called NE before, I mean, it's the size of my sample times this number density, N. So this thing is also equal to nu max, regretful notation. Remember, this one's the filling factor. If it's an integer, I got a filled Landau level. Okay, so the number of electrons, I can write it like this, EB. So my number density is just the filling factor. And I have h bar, 2 pi, so that's just E B over h. Planck's constant without the 2 pi. Dumb. So when that nu is an integer, like I said, basically I've I have to have this huge, if you will, at low temperature, huge energy gap between levels. So what that energy gap means, in terms of my Landau levels, is that, you know, my conductivity, essentially, which, you know, when I'm scattering off impurities, my scattering can be elastic or inelastic. Inelastic involves a change in energy, but all my states are filled in my Landau level, and I have a finite gap. So that mean time, basically, for inelastic collisions, goes to infinity. So that's just another way of considering that gap between Landau levels. So I don't have impurity scattering. So another way of saying it is that tau goes to infinity. And you know, I don't control the number of electrons in my sample. I control the magnetic field. So I can imagine that scattering, or that conductivity, goes to infinity for certain critical values. Of my field B. That's a hand wavy argument anyway. Impurity, scattering, and Drude model, it's just a mechanism to give sigma naught large. In the case when I have integer filling. That's all it is. So then if you look at my conductivities, yeah, I needed that. Okay. So at critical fields, the field that I use to tune essentially my Landau levels. And that's essentially the integer quantum Hall effect, the end. So in the integer quantum Hall effect, you measure that, well, you measure the resistivity, right? The inverse of that thing. So it's the resistance is the transverse. So V in the y direction, I in the x direction. That's the inverse. Call it resistivity rho xy versus B. And I don't know. Am I doing this right? Sure. There's some plateaus. And each one of those plateaus corresponds to a different integer value of nu. Say 2, 4, and so on. So the critical fields are actually these large regions of critical field. So the plateaus, so the critical are smeared out. So you have to delve into sort of impurity physics in order to understand that a little bit better. But this type of integer quantum Hall measurement, so literally magnetic field in the z direction, electric field in the y direction, look at the resistance value of these plateaus, that gives you E squared over H. To super high precision, and I forget what it is. It's like 10 to the 7 or something. And the physics, again, behind that is essentially a combination of Landau levels and then a little bit of disorder, impurity, localization that comes from the Drude model, and which also you need to explain the experiment in terms of the broadening of those plateaus. But the basic physics is the existence of the Landau levels there. Okay, so that's like the quickest and dirtiest derivation, I think, humanly possible of integer quantum Hall effect. Any questions on that? I don't know if we'll have time. I wouldn't mind talking about fractional quantum Hall effect. Integer quantum Hall effect, you're basically exciting single electrons between Landau levels. In the fractional quantum Hall effect, you form emergent quasi-particles that are fractions of the electronic charge, fractions of 1/3 essentially. The nice thing about stuff like fractional quantum numbers is that they can emerge naturally out of quantum field theory, the same thing that we're deriving. And in quantum field theory, as long as, the philosophy again is you have a vacuum and you have excitations out of the vacuum, there's really nothing that says that those excitations have to have fundamental units of charge. And that was, again, another Nobel Prize for Laughlin and others who basically described, fractional quantum Hall effect. If you look closely at these levels, they're not just integer, there's fractional values. And that has to do with essentially an extension of this type of field theory, which is relatively straightforward. If this class just kept going for another semester, we could definitely do a lot of fun stuff like that. I don't know, I'll think about it. Let's skip class on Thursday, because I'm super busy. And we'll come back here in a week, and I'll decide then. We have 3 more classes. I'll send an email so we don't forget. Hopefully I don't show up one of those days.